Today we're going to look at section 2.5, linear equations of direct variation and our word problems. Our objective is to be able to write equations that relate variables that vary directly and to be able to write linear equations from word problems. Our direct variation is just when y and x are related by an equation of the form y equals kx, and they are said to be directly proportional. So what it means to be directly proportional is that when one value increases, the other value increases. So as x gets larger, y gets larger as well. If x gets smaller, y gets smaller. So the k is our constant in this variation. So x and y are variables. Okay, so at times I'm going to ask you to write an equation that relates the variables. So I should only see x's and y's in my equation. K is a constant, and our goal is to find that constant, which is just a number, and to keep that and substitute that in. It'll never change for a specific problem. So let's look at a couple examples. Y equals 12 and x equals 4. And I'm telling you that x and y vary directly. Even though they usually write x and y, because this is very linear, we usually write in the form y equals to kind of be very similar to our slope-intercept form. So let's look at this. If I had my equation, y equals k times x, I'm just going to substitute in 12 equals k, because I don't know it, times 4. And then the only thing I can do is solve for my k value, divide by 4, and I get 3. Now, this is not my answer. This is just the work to find the constant. I want to write the equation that relates the variables. Remember, x and y are my variables. So if I go back up to my original equation, my variables are y and x. So the only thing I need to do is substitute in my 3, and this is my equation. It should look very linear, because this is y equals mx plus b, where my b is 0, so I have a y-intercept of 0, and a slope of up 3, right 1. Okay, so now they ask for a follow-up question. If x equals 5.2, find y. So I'm going to go back to my now equation that I have. Y equals 3 times my x, which is 5.2. So if I substitute this, or multiply this out, I should get 15.6. So y equals 15.6 when x equals 5.2. Let's try it again. So I give you a y and an x. Y equals k times x. I like to rewrite the equation each time just so I get used to the equation. So when it comes to quiz or test time, I've written it so many times that it's like second nature. Times 28. So I'm going to get k equals 6 over 28. But I can reduce this. So I know both are divisible by 2, so I'm going to get 3 over divided by 2, 14. So k is 3 over 14. However, my equation is y equals 3/14 times x. So this is my actual answer. And when they ask for a follow-up answer, this is the equation I'm going to use. But now they're saying, well, what if y is 10? What would x have to be? Okay. So to get x by itself, I'm going to multiply both sides by the reciprocal. I'm going to multiply by 14 thirds. And multiply this side by 14 thirds. And then write my final answer. So that simplifies to just a single x. And here I'm going to get 140 thirds. I can tell it's divided by third. I'm going to get a decimal. It's going to be a repeating decimal, so I'm just going to leave my answer just like this. So x would equal 140 thirds. Usually on a quiz or a test, though, I'm going to give it to you as a word problem. But the work we just did is the work you're going to have to see on these equations, these word problems. But we just have to write the equation first. So let's go through this first one. The height, h, in feet, and then knowing the units is important, at which a wave breaks varies directly with the wavelength L in feet, which is the distance from the crest of one wave to the crest of the next. It's kind of a mouthful, but the thing you want to look at is this varies directly. We're going to deal with actually different types of variation this year, so we know it varies directly. So we know we're dealing with our basic equation, y equals kx, but there are no y's and k's in this equation. We have h's and l's. So we kind of go in order as we read, left to right. So the height, h, varies directly, so we know we're going to have a constant times our next variable, the length, l. So instead of y equals kx, I have h equals kl. So now I can just use my substitution. It says a wave that breaks at a height of 4 feet. Well, that's my h. So I know h equals 4. Has a wavelength by l of 28. So now it's just a substitution. 4 is equal to k times 28. So I'm going to do k equals 4 divided by 28. I know I can reduce this to 1/7. So it says write a linear equation. So now I'm just going to have h equals 1/7. Now, if they give you variables to use, you want to use those. I shouldn't see y's and y's and x's in this problem. Now they ask a follow-up question. Find the wavelength L if a wave has a height of 5.5. All right. So now that I have my equation, I know that h is 5.5. I have 1/7 for my k value times L. So what I'm going to do is multiply both sides by the reciprocal, 7 or 7 over 1. And when I multiply 5.5 by 7, I get 38.5 equals L. Now that we're dealing with a word problem, I probably want to answer my question in words, so find the wavelength. The wavelength is 38.5, and if we go back up here, length is in feet. And that was the final answer. Okay. Let's try one more. The radius r in inches of a hailstone varies directly with the time t in seconds that the hailstone is in the cloud. After a hailstone has been in the cloud for 1 minute, the radius of the hailstone is 0.25 inches. So let's kind of think about, okay, here's our varies directly. So that's our y equals kx, basic problem. So we're dealing with r's and t's though. So r is equal to my constant times time. They tell me that when it's been in the cloud for 1 minute, it has a radius of 0.25. All right, so I know my radius is 0.25 inches, matches with inches, so I can try 0.25 equals constant. And then t, my time says 1 minute. However, they tell me the time in my equation has to be in seconds. So I know 1 minute equals 60 seconds. So you have to be careful with the units. So I'm actually going to substitute a 60, not 1. And that's where most students make the mistake. So, solve for k, I'm going to divide both sides by 60. So I have 0.25 divided by 60. You never leave a decimal within a fraction. Okay, so what I'm going to do is just, in my calculator, do 0.25 divided by 60. I get this long decimal, 0.0041, and then all these sixes repeating. Well, that's not a really nice answer, so what I'm going to do instead is convert it to a fraction and get 1 over 240. Now that I have that, they want me to write my equation, so I'm going to go back up. I know the radius of the hailstone is equal to 1/240th times the time that it's in the cloud in seconds. My follow-up question, it says find the time, so I'm looking for t, if it has a radius of 0.5 feet. So again, I have 0.5 feet, but they said my radius has to be in inches. So how do I do that conversion? Well, we know 1 foot, or sorry, we could do it either way. We know 12 inches equals 1 foot, right? 12 inches equals 1 foot. And a lot of students don't know, do I multiply by 12, do I divide by 12? They get kind of messed up with conversions. The easiest way to do, I feel, is if I take my conversion, and if you're on any standardized test, they give you a conversion sheet, they'll give you something like this, 12 inches equals 1 foot. I have 0.5 feet. So where does it go? Let's put it underneath the 0.5 feet, and I want to know how many inches. So I can just cross multiply, it makes it a lot easier. So this lets me know that my x, okay, and truly, the reason this works, and let me kind of go through it a little bit more for you. When I cross multiply here, I get x times inches times feet. You truly get those units to carry over. On the right-hand side, I get 12 times 0.5, which is 12 times a half, which is 6 inches in feet. Okay? So when we do this, the inches and feet, when I divide both sides, will go away. So I get x is equal to our 6 for our conversion. Okay, so if a half a foot is equal to 6 inches. Now hopefully you knew that, but if you don't, because you see a decimal and it throws you off, you can always do this conversion. So x is 6 is what I should be substituting in, or in our case, our radius equals 6 inches. Okay, so now I know my radius is 6 inches. 6 is equal to 1 over 240 times t. To get t by itself, I'm going to multiply both sides by 240 over 1, or just 240. So if I take 240 and multiply it by 6, I'm going to get 1,440 equals t. So again, I want to answer this in words, find the time. Okay, the hailstone is in the cloud for 1,440 seconds. Okay? So that's our first part, our writing direct variation equations. And since they're so linear, y equals an mx, kx, so we don't have a y-intercept, we're going to now look at different ways to write linear equations for word problems. So some keys that might help you is to write the information in the form of ordered pairs, of an ordered pair. Because we've dealt with, when you have an ordered pair, being able to write the equation of a line. Then graph the ordered pairs to help you out, and then you can find the slope. Because to write the equation of any line, especially in slope-intercept form, we need a slope and the y-intercept. Or we could do point slope, where you have the slope at any point. So let's look at this. Write a linear equation from the following word problems. In 1990, retail sales at bookstores were about $7.4 billion, and in 1997, sales were about $11.8 billion. Write a linear equation for retail sales are in billions of dollars at bookstores from 1990 through 1997. And then estimate the retail sales of bookstores in 2012. So all that information can be pretty overwhelming, but let's just break it down. Let's look at the information they give us. In 1990, the bookstores were about $7.4 billion. Okay? And in 1997, so we could do a couple things. 1990 is my time. My independent variable is usually our x. Our dependent variable is our y. So we'll do, in 1990, we had 7.4 billion. And it says in billion, so I don't need to write the billion or put all the zeros. And then I know in 1997, sales were about 11.8 billion. So those are my ordered pairs. So let's think about what this looks like on a graph. Since they went from 1990 to 1997, we'll put 1990 here, which means 1997 would be over here. Let's put some points on here. In 1990, I was at 7.4, and in 1997, I was higher at, say, 11.8. And it doesn't have to be perfectly spaced out, but just to give you an idea of what's going on. So what's happening here is that my sales are steadily getting higher, growing. But they want me to write a linear equation. This is just a line. So to find the equation of a line, and we typically write everything in slope-intercept form unless they tell us otherwise, I need to know two things. My y-intercept, which I have, there's my b value, so b is equal to 7.4, and I need a slope. Slope is rise over run. So I need to figure out how much I went up and how much I went over. Okay, so I went up, I find the difference between these, 11.8 minus 7.4, and my y minus y. I want to find out how far over I went. If I go from the years, and we want to make sure it's positive, we have 1997 minus 1990. So look, this is all I did. I took my y minus my y, my x minus my x, my change in y over my change in x. Okay, so all we're going to do is 11.8 minus 7.4, and we're going to get 4.4. And 1997 minus 1999 is 7. So what this says is we increased it $4.4 billion every 7 years. Okay, so but again, we don't want to leave our slope with a decimal in it. So in your calculator, just do 4.4 divided by 7. You're going to get a crazy decimal, convert it to a fraction, and we get 22 over 35. So now that I have my slope and my y-intercept, I can write my linear equation, where they said sales. Okay, our sales aren't our y, they called it r for retail sales. Okay, so we know r, which is kind of like my y, and let's use, let's say, t for time, is equal to my slope, 22 over 35. I'm not using x's, I'm going to use t. A lot of times in word problems, I get rid of the y's and x's because they use variables that make sense for the problem. So this is our retail sales is equal to 22 35ths times our time plus my y-intercept, 7.4. Okay, so this is my equation, my linear equation. But they asked the follow-up question. Estimate the retail sales at bookstores in 2012. All right, so this is where it can be kind of tricky. I put 1990 right here, which is actually times 0. Okay, so if I want to know what happens in 2012, I need to know how many years have passed. Well, from 1990 to 2000 is 10 years, plus another 12, so T is 22 here. So to find out my second problem, my retail sales, I'm just going to go to my equation. I'm going to substitute in 22 for my year, my time, plus 7.4. So I'm just going to type in my calculator, 22 35ths times my 22 years, and add 7.4. So what we get for retail sales is approximately 21.2. Now you might think, well, we usually don't round decimals, and I've had problems before, but this is money. So we're talking about answering this kind of question. So giving a fraction answer really wouldn't make sense for giving how much money this bookstore made. So again, how much did the bookstore make in 2012? In 2012, they made $21.2 billion. Okay, and the reason I rounded to one decimal is because they rounded to one decimal earlier in the problem. So that means that I'm going to want to round to one decimal here. Okay, try one more and then we'll be done. So from 1995 through 1996, the number of movie theaters in the United States increased by about 750 theaters per year. In 1985, there were about 26,000 theaters. All right, so I can see one ordered pair. Here's my information, my input and my output. If I input my year, my independent variable, because this just happens on its own, the dependent variable, our y, depends on what input we put in. That's why we have independent and dependent variables. All right, and we know we're starting in 1985. So when I graph this, I'm going to put 1985 right here, and they talked about 1996. So I'm going to put this down over here. I know in 1985, I had about 26,000 theaters. Now they said, write a linear equation for the number of theaters, and they're calling the number of theaters n. So that's my y in my equation. And I'm going to let t be my time. And said, let t equal 0 be 1985. That's nice. So if 1985 is 0, 1996 is 11 years later, so this is t equals 11, just for our future use. They didn't tell us how many theaters were in 1996. What they told me is that we increased by about 750 theaters per year. So every year, every time I go one little tick mark, I increase the number of theaters by 750. So I go up 750 theaters for every 1 year I step. Well, that's just slope, my rise over my run. So my slope is 750 over 1. My rise, theaters, which is our n value, and our run, time, is 1. So now I can write an equation, because isn't this just my y-intercept? So I know my m is 750, my b is 26,000. So when they ask me to write a linear equation, I'm not using y, I'm using n is equal to my slope times x, which is t, plus my y-intercept. And then they also ask a follow-up question. Estimate the number of movies in 1996. Well, now that I have my equation, I know 1996 is 11 years after my start. So 750 times 11 plus 26,000. Just take your calculator. 750 times 11 gives you 8,250. And if I add 26,000 to that, I get a total of 34,240. Again, it's a word problem. So in 1996, there were approximately, because remember, this is just a linear model, 34,240 theaters. Now, you don't have to write the approximately part. You can if you'd like, because everything in life, this isn't exactly, because it says it basically increased 750 theaters per year, but that's just an average. So this is just a model to give us a close estimate of where theaters are in the future. So hopefully you have a little better idea about writing equations that relate variables that vary directly, and that you feel better writing linear equations from word problems.